The presentation tonight is on non-destructive testing, and it's something that's not often visible. You see people pulling things off aeroplanes and putting things back on aeroplanes, but this is a really vital safety function, and it's a real vital link in the safety chain. And as we will see through by example, that there's many an accident that has been stopped using this technology and these processes. Our speakers tonight are Tony Collier. Tony began his career in the Royal Australian Air Force, and after he left the military he went on to found his own NDT company, which he's based here in Perth, and he holds a level 3 NDT qualification, which is the highest standard that you can have in Australia. His partner in crime is Scott Newcome. Scott also holds level 3 certification, and in addition to explaining NDT techniques, both Scott and Tony will give us examples of how NDT processes have averted major aviation accidents. We're very fortunate to have both of these gentlemen here tonight, and I'm sure that at the conclusion of the presentation you'll have got a much greater understanding and impression and just how vital this process is in safety, and surprisingly in adjusting maintenance programs in both directions. You can detect faults and contract the program, or the history of the item has improved so much that the life can be extended. I'd like to introduce you, Tony and Scott, if you lead us through the wonderful world of NDT.
Good evening, ladies and gentlemen. As I said, is that too loud by the way? Oh, no. It's just feeding back on me, sorry. Been in NDR Tech for, unfortunately, 45 years, and I have sort of semi-retired now, and have seen it all through the Air Force, through the civilian programs, and a lot of working with engineers during that period. I've been fortunate enough to be able to train Scotty, who's going to take my spot and has been working towards the start of his level 3 career now, so the reason why he's going to give a little spiel later on is to get him into this sort of stuff. Introduce the 5 main NDI methods and the relationship by safety by inspection from an in-service approach, so not from a manufacturer sitting in an office feeding the information out to us. This is from our perspective. That is what we did, didn't it? First of all, what is an NDT? Well, we hope, and it has not always the case. A non-destructive inspection is any inspection applied to a component or part structure that does not harm it or degrade it in the process. I have seen, lucky it was a piece of ground support equipment, put in a mag particle bench, the guy got it wrong and it blew 3/4 of the threads off the end of it. So we can destroy things if we do get it wrong. What is the purpose of NDT? As I alluded to in the introduction, the main thing is it's a safety barrier, not a barrier, but a safety assurance. We won't do a guarantee because there's no guarantees. And it can be used, as previously mentioned, to save maintenance time, and the other way is if things start cropping up, you then start reducing those time frames. And that's all done between the reliability of what we're doing and the engineers. Something that most people know about is the NDI methods, what we use, but they don't generally see the relationship between the engineers and what we're doing and how we establish and they establish what we can find, and that's that safety by inspection. Now, we're all familiar with these, and it's usually a good starting point. We're not immune, and it's still happening today, where we're getting fatigue failures of a massive scale that are enough to down an aeroplane or cause severe panic to the industry. Clearly the Comet was the first major disaster and it took them a while to work that one out. For those that don't know, it had square windows in the nicely nearly pressurised aeroplane, proved to be fatal. And the left-hand diagram there just shows how it broke up in flight. We're all familiar with the Aloha Airlines 737. These are the sorts of things that we're here to help mitigate in the future. Unfortunately, with aviation, it's progressing, so generally it's a reverse. We're learning from what's gone wrong to where we're at. Even new designs. I mean, only the other day they granted all the 777Xs, I think they're called. They had major failure in the thrust link from the engine pods to the airframe, so they got grounded for 4 months. That's a brand new airplane with the technology we've got today, but it was found before it caused any grief. And they did build a bit of redundancy into it, thank goodness. So NDT has been around since the sort of 70s in the mainstream. When I joined NDI in the 80s, it's sort of been established as a profession within the aviation. Prior to that, it was done by airframe engine type people, and it was fairly limited. And around that 80 mark when I joined, we had some really good instruments that you see on the desk there. They would have been the size of that desk when I started. So, yeah, as some people would describe me as being a dinosaur, I would tend to agree sometimes when I look at that. Generally, our NDI technicians themselves, not many people say, well, where do you get them from? Generally, we get them from Amy Lamey stock, which is your aircraft engineers and licensed aircraft engineers. So it becomes like a post-grad affair. It makes it very hard to attract people into NDI. And it's extremely to the point now where we're importing people from overseas, training from scratch ourselves as a small company with only, say, 20 odd people. Only 4 of those are doing NDI. We're having to train someone from scratch, which are totally not useless, but non-productive for at least 2 years. That takes 2 years once they're an airframe engine fitter or aircraft engineer, mechanical engineer, to be able to do NDI by themselves efficiently. We lost the battle, and this will probably, Des will not enjoy this one. AS3669 is no longer supported, which is the Australian standard for how we train, or what level we train our NDI technicians to. And it's been taken over by EN 4179 and NAS 410, so they're the American documents that are identical. They just like to have different titles on each to please the pair. So we now abide by that. And that details training hours, everything. And at the end of 2 years, we could turn out a NDI technician. CAS has still got some old regulations applicable to, say, your CT4 and your windshield, which is Car 30. You have to have CASA approved authority to work on that. So you can be qualified under that system, but you also need your CASA approvals as well. So there's a couple of different systems still kicking around, running in unison. Okay, the methods that once we've got this person after a couple of years that they should be able to do are the 5 on the left. So we've got LPI, MPI, liquid penetrant, magnetic particle inspection, eddy current inspection, ultrasonics and radiography. They're your main 5. On the right hand side, still what we call the fringe dwellers because they haven't touched us yet as the in-service predominantly, which is your thermography, acoustic emission, stereo shearography. That's done on every time a tyre gets retreaded. And for those that don't realise that most aircraft tyres get retreaded up to 5 times if they're lucky. And the shearography is done every time to make sure the carcass is okay. Holography and neutron radiography, well, they're well out there. We don't have a nuclear reactor, and the other one requires perfect stillness that you couldn't do it in a building like this. So they're ignoring the ones on the right for what we're going to be talking about tonight. We're on the left. It would be very silly of me to sit here and try and get through in 3/4 of an hour to teach you all about NDI, and you'll go to your NDI tech. So I'm going to have to be very quick to go through that before we can get into the why we do what we do and why we can't do what we can do, if that makes any sense. Okay, penetrant is easy. Basically all you're doing is increasing the visible contrast between the defect and its background. Biggest one with that one obviously is the defect must be open to the surface, and so there's a lot of cleaning and prep that goes with that. Paint stripping, it's not ideal for an in-service aeroplane if you've got to do something on the aeroplane because people get a bit tense about these paints, especially these days, and or NDI technicians are probably known as prima donnas because we don't like getting our fingers dirty, so we don't do that work. That's not our problem. So we'll just come in and do the inspection. Penetrant, really the biggest limitation, which the older people in the place will understand, is we used to use a red dye like it was going out of fashion. That quickly is not to be used on aircraft these days because it's not sensitive enough. We use a fluorescent dye now. There's a quick example at the bottom there of the bleed out you get. So the penetrant's actually got to get in and you've got to draw it out to see it under a black light environment. It's really simple and cheap. So now you qualify the penetrant. So we'll look at the next one. Mag particle basically only works on ferromagnetic materials, your bolts, anything steel undercarriages, all that sort of stuff. And basically you introduce a magnetic field into that part, and then you put ferromagnetic particles on it, which in our case, 9 times out of 10, are encapsulated with fluorescent material, and you look at it under a black light. But you're not looking at the defect in this case, you're actually looking at agglomeration of particles particle build up on the part. So if it's got a bit of plating on there, be it non-conductive or conductive, you can find it. A defect sitting straight in the parent material. Up to about 3 millimetres, gets much below the surface, a few thou below the surface, it becomes a bit hard to see. Again, it still takes a lot of experience to do it, and you can magnetise something one way and you won't find a defect, magnetise it the other way and you will, and all this sort of stuff, or you magnetise it this way and you find out you can see it a different direction. This is where it gets a little bit more expensive. You know, 70 grand upwards just for a mag particle bench these days, but they do last a while. And those two methods, which is penetrant and mag particle, we've grouped that into a process. So if you can do mag particle or penetrant, you can do any component, there's no issue. It's the same process for either or. So realistically, it's not a procedural based thing, it's a process based method, penetrant mag particle. So they're our easy ones, and they're the ones we start the boys on. And girls now. Eddy current, this is where it starts to become, if you're basically an airframe engine type person who's used to working with his hands, you better start learning electronics as well. It's all good fun. A circular flow of electrons is introduced into a conductive material, so there's its first big limitation. It's got to be conductive, but the best material for doing eddy currents on that's in the sweet spot for that method is aluminium, and it's alloys. Works the best. Doesn't work that well on steel and your other materials. It's used for general surface scans, so you don't have to remove paint if it's not too thick. Multi-layer inspections, and we've got some up here later and we'll run you through. So if you've never seen NDI before, we'll push you through some of these so you can see how they work. Multi-layer subsurface inspections, they're always good fun. Conductivity, hardness, verification, so we can actually tell you. Classic example was an aircraft fire at Janik up the other year. The aircraft next to it, they were just going to put it back in service, and I think Scotty might have saved their butt and said, well, are you going to check that one? As soon as I stuck the conductivity meter on there, it was as soft as, yeah, I've got to refrain from sweating. It was quite soft. So aeroplane skins were US. So, but an engineer had actually said that was good to go. Rotating bolt hole inspections, thickness verifications, not used very well, it's not that accurate. Skin lap joint sliding probes. Remember the old 747 in New Zealand years ago where they were using a knife down the lap joints to get the goop out, and then they would mask up and paint it, and they cracked this long bounce in the nose of an aircraft? Yeah, that sort of drove that sort of inspection. And paint thickness, we can actually tell how thick the paint is, wet or dry. So it works wonderful. Now, what we talked about instruments, and I laughed. The one on the left there, that's your 1978-80 instrument, state of the art, did everything, needle swing. One on the right is a basic, similar to what we've got up here now, phase analysis type equipment. This is for eddy current. The one on the left, as captioned, is definitely a boat anchor. It relies on a needle swing and super amount of experience. If you've never used one before, it's not a case of watching the needle. It's if the needle does this or it does that, anything, this thing's a nightmare and it'll go off at anything. The newer ones separate the variables, make life a lot easier and improve our defect detectability. We're now into the procedural methods, so each particular job basically has to have a reference standard to set up for that job, or a calibration standard if it's just a surface scan. Written procedures are the big thing for that. You've got to have a nice set of guidelines on what to do, so they don't leave it up to the technicians these days to imagine what they need to do, in theory. And it's a high skill. Again, it does take a long time. Anyone can do a surface scan, but to do the whole gamut of eddy currents is quite involved and enjoyable, I might add. Ultrasonics, this one's losing favour as its true form, where you can picture banging a sound beam in, looking for cracks running around a bolt, receiving the signal back. That's sort of losing because it's a non-tangible method and it's very hard to be consistent, and it's a black art as it's known. and it's a very high skill level. Two people can use the same probe and they'll press slightly different, get totally different results, and you've got to set it up for yourself. So it's an interesting one in its pure form. Mainly used on aircraft now for disc bonds because everything's made of plastic and bonded, so we like to find disc bonds before panels fly off these days. Part thickness measurement is used extensively when they blend. A lot of corrosion, a lot of old aeroplanes use it for blending. Once they've blended it out, you're measuring what's left, because it's very hard to get anything on either side of an aircraft skin generally where you're working, or a stringer. The encoding thickness, we've got an instrument that runs at 50 megahertz, and it's accurate to 1 mil. That's MILS, which is basically a millionth of a metre, millionth of a yard, sorry. Radiography is our last one of the main 5 methods. Basically it's short wavelength light, and it passes through matter because of its short wavelength. Basically what you're doing is measuring the absorption characteristics of a material under test. In other words, if it's thick, it's going to look light on an X-ray. If it's thin, i.e. crack, it'll look dark on an X-ray. And then it's a fairly simple process. You set up your X-ray set, job in between, film behind, bang, just like a human X-ray. Except this stuff, we don't use special high intensity filters, so there's a lot of radiation going around, and we hide when it's happening because we don't have nice little booths. It's a bit hard to fit a big aeroplane in those. Limitations, obviously it's dangerous to humans. We'll say obviously, some people may not know. It is dangerous to humans. I've had people come in and you've got barriered off, you've locked all the doors, still somehow they get in. And the first thing, of course, you say to them when you're in, you switch it off and you look at them, you come in. Yeah, are your gums bleeding? There's no relationship to anything, but you're asking that question first, and yeah, they seem to get worried fairly quickly. Defect must lie parallel to the impinging man. I had a boss once that thought once something's X-rayed, it's fine. It's defect free, fine. Fit it back to the aeroplane, it's good to go. And it's not the case, as we'll find out shortly. High operator skill required in the interpretation. It's just like being a doctor of aeroplanes. You know, you are the actual one that's actually having to make all these decisions as well as shoot them, and it's extremely costly. I would hate to think if we went to some of these digital ones that use cameras and stuff and swing around on arms, we're off for millions, but we haven't got that far. We're still using old school radiographic film, just like you may have seen back in the 80s before they all went digital. That's still our game. And this is some of the X-rays we've taken. In particular, the only reason I put this one on there is just to give you a little bit of an idea. This is a typical steel tube in an aircraft. The one sitting below it is a typical one that's been corroded. So it's chalk and cheese when you start looking at it. From the outside, these tubes looked okay. And in particular, this aeroplane, all they did was pull the instruments out, pull the engine out and tip the thing in a heap. It was that badly corroded. From the outside, it looked fine. The only thing that triggered them for us to even look at it was they found one crack on one bit of steel. Ended up being in the ditch. Now, how do we tie this into what I've just said? So we're now full bottle on raw NDI text. This safety by inspection, as the name implies, it's a safety by inspection, but when you inspect. Right? So safety by inspection is one of those things that the engineers have developed, which I've run through a few trials, works really well in theory. If it's theorised, there are some issues, but we'll get to it. It's assumed that there's a crack in the part from day one, is how they work it out, but what they want is an NDI technician to inspect that part twice before that defect ever becomes to a point where that part's going to fail and cause a catastrophic failure. Obviously, you're not going to worry about parts of a light nature, but you certainly worry about your structure of your aeroplane. You do not want a O'Hara Airlines or the Comet. You just don't, even though we're still getting something similar these days. All right. So it relies on a good interface between engineers and NDI to work all this out and actually do it. And it's expressed as a defect length, i.e. you can find using eddy current on a flat surface 3 millimetres with a 90% probability of detection, POD, with 95% confidence. Now, I'm not that great at maths, but if you start multiplying all those percentages, what's it alluding to? You're never going to find everything every time, even though they're saying you should be able to find a 3 mil defect. You may not. Now, what's really interesting is where have they got their data from for these crack links that the poor engineers are working with. So basically from OEMs, and they've spoken to or looked at mill standards and handbooks and NDI general procedures or NDI technicians. That's where these have come from. Most of them that we deal with, and here I can tell by just looking at them, may not necessarily be true. It's certainly not true in every application, and that's the big issue with aircraft. Everything's different. You can't say eddy current will find 4 mils on every account. Guarantee. That's what they're saying, with a confidence rate of 95%. 90%, sorry. May or may not happen. So, bulk hole eddy currents 1 mil, liquid penetrant 3 mil, mag particle 2 mil, and X-ray's not even on there because they can't, no matter what they try, they can't really work that one out. So, with penetrant mag particle, that's fairly straightforward. They say 3 and 2 mil. I can give you a bolt that I know you'd find very hard to find a 10 mil crack in. But that's why engineers should be approaching it slightly different along with us, which they have done, but unfortunately for the dollar conscious area of the market in civilian aviation, we don't tend to use SBI. So NDI technicians, generally if you ask them, well, what will you find? They'll tell you the smallest crack you can find. This is where they get their information from. Because pretty much honest, we can always, we would. So we'll probably tell you 1 mil instead of 4. Researchers will then ask what size should be detectable, and they'll work it out, well, intrinsically it should be able to detect this, and that works on that. Where this probability detection system would ask a different question. It's what's important, what is the largest defect or crack that's going to be missed? And we've all heard it. Most inspections that I've ever done are not backed up by a POD. Scotty's got one he'll talk about, which has. And it's really interesting to temper what I just showed you, that slide with those figures. I like this one. The book's called Have Cracks Will Travel. Look at the problem there. He worked out that most people are going to have trouble getting a 50% POD with 95% confidence for a half-inch crack. That's sort of in conflict straight away with what the published. So these poor engineers are working from a book and going to grab a figure and say, well, I can work that out, and then we get a failure because he's underdone it or overdone it. And it is a joint effort. The safety is a joint effort between NDI and the engineers. The two need to work together. The biggest problem I've got is you sit in any class and they talk about variables, and when you start mixing 5 mil, forget about it. We're dealing with reliability of NDI being influenced by all these things. So the inherent capability of the technique, so someone's decided it should be able to get this. Defect characteristics, well, they're just a couple, there's a lot more than that. This is just a quick overview, which direction's it in, how tight it is, what's going on. Bottom one there, component characteristics, surface finish, geometry, material variations. There's also a whole bunch of other ones. And the one that's really popular these days is human factors. And that then gets taken into account sometimes when we're working this out now. Equipment setup, coverage of test area, to name a few, but there's quite another one. I'm looking around the class and seeing a lot of people similar age class, sorry. Anyone heard of low light myopathy? Right. Driving along at night, daytime, you can see everything on the road still. Gets a bit dark and we start not seeing things as well as you could. Can be low light myopathy, affects a lot of pilots as well. We take our eyesight test in daylight like this and we read a chart, which I've got here, and I'll show it to you all so you can have a go at it. And then promptly go into a dark room. And older people, what do you think my chances are of seeing a defect if I've got low light myopathy compared to these young festers sitting over here? Not documented. Why? Because most people that are working this out come from the United States Air Force military, most of this jargon. They don't have young people doing it, sorry, old people doing it. So it doesn't come up on their radar. And it probably should. What is a pod trial? So probability detection trial is what it's trying to do is establish what you can find in that application, not as a general figure. So we're going to take a look at this wing fitting and we're going to work out through a number of test pieces what these guys can find. So you don't get told what your results are, you just record them and hand them off. We get a whole bunch of people of different experience levels, as many as we can get our hands on, to look at as many different scenarios of the same problem, either with different size defects in these artificial reference standards, or one's the same size, but we'll also keep a fairly heavy splattering of defect-free holes. So they're not looking at a defect every time they put their probe on something. So they've got their map it out and tell you what they've found. From that, we can plot it out. Is that absolutely concrete? No, because I don't know if any people have worked on aeroplanes in the middle of the night when it's raining and they can't fit the damn thing in the hangar. You've got to go out and do the job. Or even something as silly as your technician happens to be frightened of heights, and you've stuck him on a tailplane out in the wind that's bouncing up and down, and he's supposed to be checking this fitting. Sometimes it might not be accurate. But it is at least a step forward from what we've got at the moment, where people are just plucking figures, or in procedures we get, they just say any defect, inferring that once you've checked it, there can't be any defects in it. Whereas we all know that defects grow to a certain point before we can find them. So we need a change of thinking, because you get the classic of missed defect, and that's an adverse on the person who's just done the job. I've been on the end of that one, called into the office, why'd you miss this defect? And I'll explain that one to you when we get to it. And this is from an NDI text perspective. We always get asked, what's the smallest crack you can find? Well, 1 mil for sure. You know, we're good. But, and that's the easy response to give someone. The real question is, what's the largest crack you may miss? And I'll be perfectly honest with you, you sit there and look at someone when they ask you that question, well, it's offensive to start with, and you go, well, I don't know. And that's what the pod trials are all about. Yeah, it's a defect sizing for any particular application. Yeah, you can play with a piece of string, it'll be somewhere in there. So why do we need the pod trials? Well, it helps the design engineers, and it does, depending on how well you set up your pod trials, with critical inspection regimes. It's not for the run-of-the-mill stuff, it is for critical stuff, and we've seen a lot of critical stuff over the years that still needs inspecting, whether it be new aircraft, or in this case, we have a lot of old aeroplanes running around out there. So at the moment, generally speaking, you're at the mercy of the expertise of these two. Alright, so just as a brief one, factors, or the main factors, they're not all, affecting defect detection are material type under test. Some materials, as I alluded to before, eddy currents works really well on aluminium. Surface condition of the test area, that can have a huge impact. Rough surface, smooth surface, perfect finish. You know, like in an engine, you could be looking for a dot, and that's your indication. Whereas if you've got, say, a rough engine casting, you're going to be lucky to find a 10 mil crack amongst all the mess of this so-called case that was built in 1932. Accessibility, that can really crunch you down. Type of defect you're looking for, whether it, well, obviously, whether it's small, large you're looking for. The smaller it gets, mind you, I will add, the more chance you've got of misrepresenting. You will probably put, when you do your pod trial, you'll get a false negatives all the time, or false positives, sorry. You will get a few of those in the test, the smaller you make the defect. Inspection method used, equipment, obviously. You've got, I can tell you now that the eddy current sets we've got these days compared to that boat anchor, it's about a 2-to-1 hit rate on smaller cracks. You would find twice as many cracks with a phase analysis kit as you would a needle swing. And this was used as the test piece, and this is the one that they missed half the cracks in this using that needle swing instrument. So things have improved with time. Reference artifacts, this is a unique one. We don't always have cracks, and 9 times out of 10 we don't have cracks. So we use an EDM slot, which is about 2 or 3 thou wide slot. We cut in at a certain length into a reference standard to simulate a defect. It doesn't. It's a starting point, but a crack will not react in the same manner as an EDM slot. But just about all your trials are done using EDM slots. All your setting up to find a defect is done using an EDM slot in a reference standard. Alright, so we'll just break them down a little bit more. So the surface condition of a part is one of the elements that does tend to change, and it's a biggie from one job to the next. So you've got the same procedure, and I don't know if you've had much to do with, say, aircraft wheels as a bad example. Some are quite smooth, other ones come full of corrosion or anodizing is quite bad, or half missing, or half on, depending on which way you are. So the actual part will change from the same inspection. So we just mentioned we set up the cowl block with an EDM slot. Wheel bead seats are an example. We went through penetrant of wing bathtubs was a classic, and this one. The part surface condition on the B200 in the 90s was take the bolts out, clean up and do the penetrant. We mentioned earlier about paint, doesn't work through paint. OEM decided you will not take the paint off. What colour's the paint? Yellow. What colour's that penetrant? Yellow. What chance have you really got of reliably finding a defect in a wing fitting? Very difficult. They eventually changed after telling us that don't tell them how to do aircraft maintenance. And that's now luckily required to be removed. And to that end, Scotty did find a cracking one the other week, which is a good thing. It only holds a wing on. Accessibility, that can severely impact the result in an NDT inspection. And when you're doing these trials to establish what crack length you got, it's very rarely they're going to stick you in the real situation. It's usually done with a reference standard sitting on a bench. So these are things that generally aren't considered. So when you get yourself jammed into contorted into a tight spot, it does have a bit of an effect on how good you are, especially if you're trying to view it via a mirror while you're doing the job. And honestly, if you've ever tried that eddy current probe in your hand and stuck upside down with the mirror trying to move your probe where you want it to go, that can be quite interesting. Viewing the inspection area via a mirror we've done, if these conditions were not simulated during the establishment of a pod threshold, it's highly likely that that probability detection trial may be larger than they come up with. Type of defect, reference artefacts. As I said, we use an EDM slot and it has no bearing on a crack. What I've got there is we came across stress corrosion cracking in a BAE 146 spar. Now X-rays is crappy at finding stress corrosion cracking. The inspection for the whole spar, main spar, was X-ray. And I'd just come off of working on the PC9 at the time, and we were trying to X-ray for stress corrosion cracking and decided it wasn't much chop, but I used to get occasionally little brown line. And I picked up this X-ray on this 146 and looked at it, and there's this little brown line dead straight off of a rivet about 3 mil long. And I went, it couldn't be, because I'd just come off of spending weeks working on this sort of rubbish. So grabbed an eddy current set, walked out to the wing, 200 cracks. None on the X-ray. So the OEM picked the wrong one. Doesn't matter how good we are, you're never going to find a defect if you pick the wrong method. Right. The other thing is, and I'm not sure of the name they give to this, but the OEMs around the world will tend to dumb it down so the lesser countries can use, say, penetrant in lieu of eddy current because they may not have eddy current, so they'll put penetrant in the book instead of eddy current. And in the old days, it was easy for us to look at that and go, well, eddy currents is more suitable, we use that. But because of the way the CASA regulations are these days, you're going to shoot yourself in the foot if you do that sort of thing. But they do dumb it down, and the biggest dumb down they do is they always pick penetrant for doing a steel inspection on, say, an engine frame. It's absolutely ridiculous, you won't find anything. Equipment used, that's our plate down there. That's a B200 horizontal stab fitting, there's two, one top and bottom. They thought they had corrosion until I went in there with the eddy current probe and there was cracks all over it. Nothing ever came out of that one, so I'm not sure what went on. That's the only one we've ever seen, and they've never ever been tested since. And this is where the Hocking Locator 2, which is similar to your phase analysis over there, found the 7 defects, and the old boat anchor I was showing you, the needle swing one, she only manages 4, and that was with 4 people. I didn't warn them, but they all agreed because their boss didn't want to buy one of these, and I was trying to convince them that they needed to. They all went back and were not happy with their boss until he bought a new one. Human factors, well, we could go on for weeks with this one. Now, remember that old 737 that lost its lid, the old Airlines convertible? Well, what ensued from that was an eddy current inspection of every fastener across the lid of that aeroplane, all right, of every 737 in the world, which is brilliant, except for the NDI technicians, because the more you do in the one hit, the less reliable you're going to become from a probability detection point of view. So if you've asked to inspect a group of 6 rivets, I'd be pretty happy with that. If you are spending day after day scanning rivets endlessly across a fuselage, what do you think that might do to the probability of detection? And that sort of thing really wasn't taken into account. They just, changed every 4 hours. They bundled it off and put a new one in there. And we talked about low light myopathy as well as another human factor that we've had to deal with, or having to deal with. And these guys laugh at me, just call me old, but it's a fact. Your eye builds up this sort of opaqueness inside, and you can see quite well in the daylight. Get yourself in a dark environment, even with your glasses on, and it's not as good. Greg knows. False positive results. Why is that important? Good old dollar signs. We're talking about commercialism here in the companies. False positives is one of the last things you want to see. But what drives a false positive generally is the smaller the defect you're looking for, the higher the chances are you're going to start getting false positive indications. You're seeing stuff that's not there. The force wasn't entirely with lip that day. And we get that a lot where you're doing a pod trial, people will get quite a number of where they're ticking something when it's actually not there. And of course, what does that do? Grounds the aeroplane for a start if it's a false positive. The cost of repairs to find out that it's not actually a defect. And a classic example was a west wing, this is many years ago. Horizontal stabiliser spark was a visual indication at the time. They saw it, got someone in to do an eddy current inspection, said, yeah, sure, it's stuffed. It wasn't, was it? So that company lost its lost all its money because the company sued them because it cost them $250,000, I think it was, to replace that spark. So the company didn't last long. High stakes game as well from a financial perspective, not just a safety one. Defects that get missed during inspection. It happens. We have to live with that. But unfortunately, it's a very negative connotation because, as we said before, I would say 98% of all the inspections I've ever done for civilian aeroplane are not underpinned by a probability detection trial. And using the term missed means I've done something wrong. And that is how it is viewed to this day by most people. First case there was a small diameter wheel bolt. We have quite a lot of those filed. It's very hard, almost to near impossible, to see defects in the bottom of the thread in a very, say, 1/4 inch bolt. It's very hard. We have one where even an engine crankcase, I missed a crack, it was 10 mil long in it, and it wasn't until they then cleaned it properly that it's popped as a letter. And of course I was at fault for that, even though the penetrant just didn't get in. Because we're not responsible for the cleaning. It's a very touchy area. Who is? They tell you they've done it properly, but apparently had like clear varnish all the way through it, so the penetrant couldn't get in, can't see it. But then they cleaned it afterwards, don't ask me why, properly, and then found this crack. What's this? You're an idiot. You're not an idiot. And case 3 was a good one, a ladder plate on a Dash 8s where the access panels are on top of the wing. There's a lot of screws, and they hold the anchor nuts in there to keep the fuel tank sealed with these little, what are they called? The anchor nuts have these little rivets, 2 of them each side of the hole. And this was around a corner. It was black to look at, and when you scan there, I knew they were there, and I got this indication. Oh, what's the rivet? I know it's the rivet, they're there. Anyway, they had to do some sort of blending repair. So they blended it back eventually. It's beautiful. What's that? Because we had to come back in and do a second scan. What's this? That's a crack. You just checked it last week. Yeah. Should I have found it? Who knows? No one ever did a pod trial. Was it clean? No. So the surface conditions straight away through it. So pod trials, as we've said, are for critical NDI inspections, not the norm. In civilian aircraft, as I said to you, unfortunately, or fortunately, I don't know, pod threshold is not published, generally speaking. Was it published for your one, Scotty? And generally not done, I'll be perfectly honest with you. If I was to write a procedure for anything that we have to, it'll just be submitted, it'll come back as a tick in the box and approval. A procedure acceptance rejection criteria may state any defect indication is cause for rejection or similar. It's again inferring that once it's done, there's nothing wrong with it. It reinforces the myth that once a structure has been inspected, it's crack-free. I can honestly vouch for you, I've had people that believe that. I also had a guy say to me, when I told him it was crack, he goes, "Don't believe you, I can't see it." Well, that's why I've got a job, thank you. But anyway, And if an NDI technician misses a defect that's below the reliable pod threshold, which we don't know about, feathers are still going to fly in the quality departments. No offence, Greg, but that's a fact. Wing fitting was another classic. You can get some OEMs that will drive you into pulling your hair out. We had one where they asked us to look for a defect, and they made the reference centers so it's all beautifully packed and everything, and it was about this thick with eddy currents, and this tiny little defect with a big steel fastener shoved in it. And I tried for ages to find this defect on the reference stand, couldn't find it. Fed it around to as many NDI techs as I could, even send it over east. Long story short, no one could find it. It was clearly evident it just doesn't work. This is an OEM procedure. And I rang them and they said, oh, well, this was written by this other company. So I got hold of this company, got hold of the NDI tech, which I happen to know, I've met him in Singapore. And I said, mate, what's going on? He goes, basically went through. I said, we can't find it. No one can find it. He goes, well, we could click. That was the end of the conversation. So here's something that I would recommend. You know you've got yourself, or an NDI tech knows when he's an NDI tech is when he says no. Right? So a good NDI tech knows when to say no. So I just squared up to the Singaporean Air Force and said, not doing this inspection, doesn't work. Well, doesn't go down too well. Anyway, they canned that program very shortly thereafter. Now what we've got to do here, I suppose, is establishing the detection miss. An important note, and we need to remember this, don't we? The NDI technicians always find the smallest possible defect every time. These guys will vouch for that. Alright, so establishing the miss now is that previous statement is obviously wrong. Once a part has been inspected, it's crack free is also wrong, along with the rest of this. EDM slots are representative of cracks, so they're not. All cracks respond in the same way, which they do not. False positive indications don't occur, they do. All operators have the same skill level, or they don't. We've got new guys, people like me, old with, say, some eye deficiency. All approved procedures are accurate. Now, we're always taught when we sit exams every year to say that you have to believe the OEM data, it's always right. I'm telling you now, a lot of it's not. All approved quality departments expect a certain failure rate and are usually well versed in pod factors. Not true either, hence the feathers fly when something goes wrong. When I say goes wrong, goes undetected, I like to use that word. So there's this huge relationship between the engineer side of it and the NDI technician, and there's so many variables from here to here, and at the moment we're winging it. Ultimately we are still winging it because we're using good equipment, good NDI technicians, but ultimately when we go to do a job, we really don't know A, what's a critical crack, and B, what's the smallest we're going to find, or what's the size defect that we should be finding reliably. We don't know that. And the guessages, is the best way to put it, that we get given are generally well underneath what the actual truth is. And if the engineer's betting his career onto the fact that those figures are correct, that's probably why we get unscheduled failures well before they're supposed to happen. Right? NDI techs have done their bit, possibly not found a few. Instead of 2, it might take 3 inspections to find it, but between the second and the third inspection it's failed. Right? So it can happen. And I'd just like to bring some OEM claims out that I've had over the years, and because we've got a light environment, because we all like to fly occasionally. I mean, I'm shit scared of it, and I still own an aeroplane, well, sort of aeroplane. Wing spar inspections on an aircraft. I won't go into the manufacturer's names, etc., because that's just not right. They called me a Colonial, and I was, then they came out, and the statement they said was, what does your NDI technician do during the day? Work on railway sleepers and then come here in the evening and stuff things up. He used a few more expletives than that. And I was sitting in the room and I didn't know what to say. And the engineer who was in the room, because we worked together, looks at me and says, oh, have you met Tony? Alright, so then I grabbed him by the scruff of the collar, not literally, took him out to the hangar, and of those 200 defects, I'm guessing what aeroplane is now, of those 200 defects, you could see one. Just one. Stuck their noses in there. Look at that, because they thought it was just corrosion. It wasn't. It was stress corrosion cracking on a massive scale through a number of aeroplanes. And they went to the corner hangar, They had a discussion that we were not privy to. Then they walked around the outside of the hangar, and that's the last we ever saw them. They were supposed to be there for a few days longer, and it took 6 or 7 weeks for them to respond with any sort of what's going on. That S211 wing fitting, we've already spoken about. Engine crankshaft's another one. Dev's going to attest to this one. It's basically, don't tell Americans how to maintain aeroplanes. We're Australians, we don't know our place. We did write a new procedure that worked though, and got it approved. Bathtub fittings, they eventually caved on that one. And a legacy aircraft, an NDI technician should be able to work it out with the response. And that's 2025 for that last one. And Scotty will explain that one in a bit more detail. Right, we've probably all seen this, but this is a classic where you move out a hurt pilot in our midst. What this is an example of, this was a known defect that caused this. The centroid risers in the Hercules, they've always cracked and they've always been checked, yet something went horribly wrong there, and that's why those wings came off that one. Food for thought, ultimately it's what we don't know that's the problem for us still, the age-old aviation problem. So I will now hand over to Scotty, because I've probably spent more time than I should have up here, but thank you for your attention. As I said, I can't make NDI texts at the end of your day. Don't be too scared about flying, unless it's with Delta Airlines like or something like that. But anyway, thank you.
Good afternoon, Engineers Australia. My name's Scott Newcome. Thanks for the introduction earlier. Just a bit of background about me. I'm a fixed-wing lamey. I was working in general aviation for about 10 years before I moved across the dark side. And I've been working for Aerospace NDI and been an NDI tech for coming up on 13 years now. And as Tony said, recently stepped in a level 3 role. Definitely a lot of experience along the way working with these two gentlemen here. So today I'm going to speak about 2 specific instances that happened recently, or fairly recent for the first one. Both are a good example, both relate to what we've been talking about here today in 2 different ways. The over-cautious, the best way I can summarise it is one is OEM who's over-cautious, taking far too much precaution and causing a lot of financial strain and other difficulties I'll talk about in a minute, and the other is too blasé, taking too much relaxed stance on aircraft maintenance and NDT. So the Sikorsky first instance I'll talk about today is the Sikorsky S92. Now the S92 is what we call a rig hopper. So Western Australia has pretty much all of the S92s in Australia are based on the west coast of Australia. Typically they're 10 to 12 seaters, and they're used to transport rig workers from the mainland out to oil rigs. There's a few other applications, but that's their primary purpose. In August 2021, not here, overseas, a pilot departed a port and reported sluggish controls during flight. That was the best explanation he could give at the time, but they knew that something was wrong, and luckily they had the good sense to ground the aircraft. They didn't actually complete that flight, which is astonishing, good really, what ended up happening was engineering dragged this into the hangar thinking, oh, pilots being pilots, there's probably nothing, and they ended up having a good look at this main rotor swash plate. Now that's the part that controls your main rotor pitch control. Engineering discovered visually, very easily, extensive crack where the pitch actuators control this big plate, which is about as big as this table, so it's a big piece of aluminium. It had cracked approximately 90% of the way through. So that helicopter may have lasted 1 more flight, 10 more flights. Yeah, pretty scary. So that launched, there's an example there. So that was verified with liquid penetrant. Yeah, that launched Sikorsky launched into their own Collier investigation, obviously, and this portion down here, where the pitch link rods attach, that's what we're talking about down here. So Sikorsky themselves, their design engineers who work within the company, established an inspection interval based on theorised propagation rate. Now, I've heard this from multiple sources, and it's unsubstantiated, but I heard it enough times to believe it is actually true. In their hurry in their nervousness, I'll say, and hurry to release a corrective action, and in the hopes of this not becoming a worldwide issue, they released a alert service bulletin just a couple of months later in January 2022. Now, this affected every single S92 in use across the world. So this is worldwide. Quite an extensive document, and some extracts I've put up here on the screen. So it's high frequency eddy current. So as Tony said, aluminium and eddy current work fantastically, and high sensitivity, and it's an extensive inspection of all of the critical parts of the swash plate. And again, keeping in mind that this particular part is about the size of this table, it's quite an extensive inspection. It takes about, we've got it down to about half an hour per aircraft, but that's only after 3 years of doing these things essentially every week. So this eddy current inspection, Sikorsky in all their wisdom, decided that this inspection interval will be every 50 flight hours. Now, most of the Sikorskys that leave our western shores will do between 35 and 50 hours in a week. So we suddenly found ourselves in the middle of a worldwide AD, or SB, with weekly trips to Karratha, Broome, Onslow, up and down the west coast, inspecting these machines, these wash plates. This is multiple machines for multiple operators, so it's a lot of work. Once a week at least. Other than the obvious, the major difficulties also include the cost involved and the downtime of having technicians having to fly around the country and fatigue inspecting all these aircraft. A question that I'm quite often asked with relation to this inspection is, why didn't they just change the swash plates? Now, as of when last approached about this subject, the OEM said that there are none available in the world. 0. So this is the fix for now. Aerospace NDI, between all of us, we've been supporting this since the SB's inception 3 years ago. No aircraft in the world since its inception has been found with a crack. So circling back to the fact that there was no POD trial performed, I can only speculate on that. I shouldn't say there wasn't. We believe there wasn't, and very little care was put into this ASB when it was released. 3 years on, no defects at all. Every 50 flight hours, if we're doing, most of the aircraft on the west coast are doing 50 flight hours a week. We're 3 years in, and most of the aircraft are performing 2,500 flight hours a year. So there's some pretty big numbers.
And Scott, just from a commercial perspective, is the OEM covering that cost, or is it being borne by the operator?
That's a good question. I believe they're covering some of the costs, and by that I mean a small percentage. That OEM has been bought out by a larger company, and it is getting increasingly difficult for the operators of this aircraft to get support. parts, etc., etc. So yeah, let's skip ahead to the next example I have for you today. An aircraft that operates out of Perth Airport and Jandakot Airport requested an NDI inspection on a horizontal stabiliser for fatigue cracking. Now, this aircraft is quite old. The original manufacturer went out of business in the early 90s, which I think I put up. The parent company purchased this as a legacy at that time in the 90s. So essentially just providing after-sales service and parts for people who operate this aircraft. Yeah, very little support is given. It's very difficult to get parts and any sort of engineering questions out of this OEM. When we were approached to perform this eddy current inspection, the OEM data, the eddy current procedure simply stated perform ECI eddy current inspection. Now, without going too much into it, Tony touched on it earlier. We can, with phase analysis eddy current machines, we can set up our machine to be incredibly precise and pick up 1, 2, 3 mil defects easily. On the other side of the coin, we can desensitize it to scan large areas with less sensitivity. Now, saying just perform an eddy current inspection just isn't acceptable at any level in this day and age. The cowboyness of that statement, it astonished all of us. Very abrupt email I got back from this OEM was a level 2 should be able to figure it out. So, yeah. The main concern there is if a level 2, okay, any level 2 across the world, you could have someone in America who thinks that it's not a particularly important part. They'll wind the sensitivity right down, scan the whole thing with very little care, and their probability of detecting a 3 mil crack is next to 0. On the other side of that, we could wind the sensitivity right up, and we would spend hours and hours in scanning this one part to get 100% coverage, looking for 1 mil defect. There's zero consistency. The procedures should be specific so that you get consistency, so that we establish a norm, and the sensitivity needs to be given so that we know, it gives us an indication of what size defect we're looking for, and how hard we should be looking in this particular instance. Tony's happy to answer questions as well, obviously. Yep.
How much information sharing is there between the manufacturers? Like you're saying, if you're told go and find a crack, is there a service bulletin or a directive that shows you where to apply your testing? Obviously, it's time is money, right, for everyone.
Yep.
And if you have history experience from someone who found it, and they give you, all right, this is where we went, this is how we found it. Everyone else could do that rather than reinventing the wheel. Does that happen in your industry or not?
Yes, largely it's driven out of the manufacturer. They will have done stress analysis, or they have experience in finding cracks in one of their high time aircraft, and they'll implement a inspection interval based on that. Often we'll also be called out for what we call ad hoc inspections, so stuff that an operator has found in the operation of that aircraft over time. Obviously things wear out, and things that the OEM haven't come across, so different environments, like where a lot of our aircraft land on dirt strips out here in stinking hot rural Western Australia, which the OEMs might be in a totally opposite environment. But yeah, mostly it's driven from the OEM, scheduled inspections where they know there's defects, and then other things like the Sikorsky example. They found a defect and then they implemented a worldwide service bulletin. So you will comply with this and inspect the aircraft every 50 hours in these areas. We've found an issue.